Alrighty, thank you for coming to the third session of the day. Today we have Andreas Moll presenting here. Andreas is the leader of the software engineering team at the Australian Synchrotron in Melbourne. His work comprises the development of data pipelines, management and analysis tools. Before being allowed to spend his days writing Python code and learning about microservices, he had to go through a 6-year Fortran and C++ boot camp in his PhD. He's going to present about Lightflow, a lightweight distributed workflow system. Please give him a warm welcome.
Excellent, thank you. So yeah, I'm going to talk about Lightflow, a distributed workflow system that we developed. And I'll start just by talking a little bit about me. So I'm originally from Munich in Germany, as you can tell by the accent. And my background is in high-energy particle physics. So I'm used to deal with a lot of data. And so I came to Melbourne mainly because for its weather, probably more likely because for my partner, and in order to develop scientific software in Python at the Australian Synchrotron. And so the picture on the left, that is what the Australian Synchrotron looks like if you had a drone, which I don't. It is a national research facility. It opened about 10 years ago. And since 2015, we're part of ANSTO. And ANSTO is the company that runs the reactor up in Sydney. We are located in Clayton. That's in the eastern suburbs of Melbourne. And maybe you've heard about that area because Monash University is really huge there. OK, so if you were to take off the roof of the picture, that's pretty much what it looks like underneath. So what we do, we have a particle accelerator in some sort of similar to the LHC, which you might have heard. But we have only one, not two. And we accelerate electrons. And we accelerate them to almost to the speed of light. And so the green trajectories paths, you can see that is where we accelerate our electrons. And then we store them in a ring using magnets. And that is what it looks like. So those yellow boxes are the magnets. And they accelerate the they keep the electrons in the ring. And when we do that, we produce light. So this is actually what we're interested in. We're not interested so much in the electrons. We just use them to produce the light. And we produce light which is 1,000,000 times brighter than the sun. And then we use that light to perform scientific experiments. Currently, we've got 10 experimental stations, which we call beamlines. And you see those gray boxes in the picture, and that depicts those beamlines. And at the moment, we're producing and storing about 1 petabyte of data every year. So that's what we're dealing with. So what do we do with the light? Here are a few examples. Everybody likes dinosaurs, so do we. And so that is computed tomography. So we take a fossil, and that's a fossil of a dinosaur that was found in Victoria. And then we can do a full 3D reconstruction of that fossil without breaking the skeleton that's inside the rock. Then we can remove the rock after we scanned it. And then we can use that, for example, to 3D print. And then you have a 3D printed dinosaur without having to damage the whole rock. Or we do a lot of work in drug development, cancer research. So that, for example, here depicts Alzheimer's research that we do. Another one that made it into the media last year, I guess, was Edgar Degas' painting, Portrait of a Woman. So that's a painting where, for a long time, people have suspected there might be another painting underneath. Painters very often overpainted their canvases. And so what we can do is we can shine the light in order to reveal layers underneath the surface that you see. And we've done that. And not only you reveal the layer, you also get the chemical composition of what there is underneath. And then you can use that to get the colors that the painter might have used. And indeed, we found that underneath. So actually, it's upside down. So I just rotated for you. And that's a person that we believe to be Emma. And that's underneath that painting. So that's the kind of work we do. While all these things use different techniques, they have one thing in common, that users want to get really quick feedback. They perform the experiment. They don't know how it's going, give very quick feedback so they can then optimize their parameters and re-perform the experiment. And that means we need pipelines. We need workflows for those users. And this is what that, in a very abstract way, would look like. So you have up there, your motivated, well-funded, curious scientist brings a sample on site. We put it into our light, which we call then the beam. And then depends on what we're looking at. We do different things happen with the light, but in this particular case, It's scattered. We have a detector behind it, very much similar to a camera that you know, a detector which writes files. We literally just write files. And depending on what kind of detector we have, those files can be a few but huge, or small and hundreds of thousands of files. They go into our storage. And then what we would like to do is every time a new file arrives, that's the green box, we would like to start a pipeline. And that pipeline, say, for example, reads the files, reduces the data, reconstructs the data, performs some first course analysis, and then presents that result to the scientist. So the scientist can then make an informed decision of maybe I have to change the parameters. And because you do it very often on a file-by-file level, you want to store intermediate results. For example, if you average over something, you have a rolling window of some sort, and so you want to have a central data store. So if you look at that, so you identify in that workflow, you have a service-like part. That's the green bit that watches for the file changes. And you have a pipeline-like part. That's the row underneath. And so what you want in there, that's what we were looking for, were task dependencies. You can exchange data between tasks, and you can keep the data from previous runs. So that means our wish list for a pipeline or workflow system is Python to start with. We are a Python shop. We have a lot of C++, but Python is what we really love. We only want a few dependencies to keep it simple. It should be infrastructure independent, so a scientist can run the workflow on the laptop, and then we can go out and put it on our computing cluster. The essentials that we were looking for when we were evaluating different frameworks were the dependencies between tasks, exchange data between tasks. It should run locally with minimal effort on a scientist's laptop, but then we can run it, as I said, on a computing cluster. The workflow should be easy to describe, because what we actually want to have is that the scientists are able to describe the workflow. They are the domain experts. They know what they want to do. I don't. And as I said, we want to have a central store for workflow data. And we would award bonus points if that system uses parts of our library database stack that we typically use. OK, so we went out and had a look of what's there. And oh boy, there is a lot out there. So every time I thought I had seen most of them, I find a new one. It's incredible. So what I try to do is typically to sort them into 3 categories. So there are scientific workflow systems, very generic, have been around for a long time. And those examples, by the way, are by no means complete. It's really incredible how many tools are out there. Then there are domain-specific systems, which actually started out very often from an algorithm or from a tool and then developed in the pipeline. And they come from bioinformatics, geology, and all these different domains. Then you have those what are called ETL, extract, transform, load. Airflow, Luigi are things that you might have heard, fantastic tools. And then there are many, many systems and libraries to do distributed computing. So we went through as many as we possibly could in a couple of months, and we found that some came really, really close to what we wanted, as you have seen what we were aiming for. But we always found that one or more showstoppers, and it would have been a tremendous amount of work for us to integrate it, or it wasn't on their roadmap or something like that. So we did it the Australian way and had a crack at it. And so the idea was just use existing Python tools, just get inspired by all these workflow tools that we evaluated, and just write the minimal code you have to do to glue all these fantastic libraries together. And that is what came out, Lightflow. So we have sort of 3 pillars that underpins the whole thing. We have the workflow description. And as you have seen, we have those task dependencies. So what we want to model it is what is called a directed acyclic graph. We went for a Python workflow description, so there's no domain-specific language in there, which means that the scientists which are already trained in Python can just use that. And they can use their favorite libraries as well, because very often they already come with libraries from their collaboration or from their domain that they want to incorporate. And we used, the libraries we use for that is NetworkX to describe the graph, and to describe the workflow, which you will see later, just the Python standard collections, nothing fancy there. We want to have it distributed, so we opted for a worker-based scheme, and we serialized the data that we sent from task to task and from worker to worker. And so for worker-based, we use Celery, and to serialize the data, we use Cloud Pickle. everything's underpinned by a simple infrastructure. So we focus on Linux as our main platform. We use Redis as a broker for the worker-based scheme. And we use MongoDB as our central data store for this intermediate data that I mentioned earlier. And that's a high-level overview of how we describe it. So you have a single workflow, and then each workflow has one or more of those graphs. And so you have the directed acyclic graph, which is shortened to DAG. And then each DAG describes your workflow with your tasks in there. And so in this case, we have two, a blue one and a green one. And what we allow is that a task, for example, say task 3, is allowed to spawn a DAG. And by that, we introduce dynamic workflows that change based on conditions, based on things that, for example, happen in task 3. Each DAG itself is fixed, so you can regard them as building blocks of your bigger workflow. So distributed computing is really hard. And so we decided to not write a central daemon. And so what we've done instead is we just said, OK, we've got those workers. Let's just use them. And so what we do is we have a worker that deals with workflows. So every time you start a workflow, we just push the whole workflow onto that worker. Then the worker does the job. And if you want now to and then it executes the first DAG, the first graph, the blue one. So it pushes that to a worker that deals with DAGs. So that's what the blue one ends up with. And then the worker that deals with the DAGs then goes through and executes each single task. And then you can have multiple workers that deal with those tasks. And then I already said that task 3 might be able to start the green graph. So once this happens, it goes onto the worker for the DAGs. And again, this one then schedules your tasks. And by doing that, we just use the worker structure. It's really easy to scale. You can say, OK, I want to have more workers to deal with DAGs because I'm constantly spawning things. So you can just scale that horizontally. There's no central daemon. There's no single point of failure in that system. So after we've talked about what it is, let's talk a little bit about how we describe the workflows, because that is actually the interface to the users. And we spend quite a lot of time to get this to a minimum so we can really easily get it to our scientists. So as I said, we describe the workflows in Python. And they can be in a single or multiple files. Scientists tend to love their single long files. So this is what we support here. And we describe the edges in your graph, so those arrows that you saw, just using a standard Python dictionary. So your key value pair turns into a parent-child pair. And I'll give you an example where we would like to have a sequential workflow where we increase a number. So task 1 starts with 0, increases it to 1, gives it to task 2, and so on. And this is how we do it in code. So we create an object, a DAG object, that we offer in our library. And then it has a function called define. And then you see it's just a dictionary where you have task 1 followed by task 2, and then task 2 followed by task 3. And that describes your workflow. So what is this task 1 object or task 2 object? It is just a Python task. And that's one of the standard tasks that we ship with the library. And that's your most powerful task you have, because the only thing it takes is a name, whatever you fancy, and a function or any other callable. And then you can do whatever you like in that callable. And in this case, we just want to increment a number. So that is what the structure of that callable looks like. So we have 4 parameters. We have the data. That's the data that we exchange between the tasks. So when you call that, when you go into that function, the data consists of all the data that comes upstream from previous tasks. Then you modify the data, and then it's getting pushed to the next of the successor tasks. The store is a reference to an object that holds all the functions to talk to the central data store. Then we have a signal, and that is in order to do inter-task messaging. And also, for example, that's the one where you say, oh, I want to start a new DAG system, start a new DAG, please. And then we have a context object that gives you a little bit of context around your task, which worker is running on, which host it is, and so on. So how do we implement this in our sequential simple example? Very easy. So again, you see the same structure of the function. And because I'm using the same function for all 3 tasks, I don't know which task it is. So I'm initializing it in the first if statement, where I say, okay, if value is not in data, and data behaves like a dictionary, then I'll just set it to 0. And then I'll just increment it, and then I'll just print something. And just print the value. And I use the same function for all three, and this is how you increment a number in a really easy way. And because it's pure Python, it's really easy for a scientist to implement any kind of logic in there. Now we talked about a sequence, but what if we want to do parallel? Something like that, where we have a branch task that branches out to 3 tasks and then has a join task where they all come together. We do it with a list. So instead of having the value being a single task, we just have a list of tasks. And that is how we do the fan out into multiple parallel tasks. So in this example, the branch task goes to the 3, lane 1, lane 2, lane 3. And then lane 1 goes to join, lane 2 goes to join, and lane 3 goes to join task. And this describes that graph on the left. But sometimes you don't want to necessarily branch out to all 3 if you have a model that, say, for example, something happens, and you only want to go to lane 2 and lane 1 and lane 2, and you ignore lane 3. How do you do that? Very easy. So that's, for example, your branch task definition. Again, it's a Python task. And as my callable at this point, I call pick lane, and that's the function. And instead of usually, if you modify the data, it implicitly returns it to the next task. But you can also do it explicitly, and that is you do it with an action object. So you give to the action object as a first parameter the data, and then it has a parameter, an argument for the limit. And so you can limit the following tasks to the ones you enumerate here. And so in this case, lane 1 and lane 2, and so it would not go to lane 3. And by doing that, you can have dynamic workflows that, depending on what, for example, in this case happens in branch task or anything upstream, will modify where you go. I talked about the central data store, and that is a drawing from the examples that we provide. And so in this case, I only would like to talk about the modify task as an example. So again, very generic Python task. We have seen that. And so the modified data in this case uses the store object. So we're not using data because we don't want to pass anything to the next task. We just want to modify the central store. And then in this case, and it has methods like get, set, push, and so on. So in this case, we get an object called image, which is nothing else than a NumPy array from that central storage. And then we just print its dimensions as you would do with a NumPy array. You can set a number. So that would set the field number to 10. And then you have a function, in this case push, where you can add elements to an array. So which means that if you have multiple tasks running concurrently, they can all talk to MongoDB at the same time and adding elements to arrays and averaging numbers. And this is how you do this. Averaging, for example, over the lifetime of a workflow run, over multiple runs of DAGs. So if we go back to the sort of abstract example that triggered that idea is, and we identify the individual parts, you see the green one, that could, for example, be modeled in one DAG, which runs, say, a single task, to keep it simple, with a loop, and that just checks for new files. So typically, if we do that, we use inotify or similar systems. And then you would have a second DAG, and that would be your processing workflow. And then DAG 1, that task would be like, oh, there's a new file. OK, I start DAG 2 and process that file. And you can have this whole description in one single file if you really like to, and it's all written in Python. Now let's go to something else, and that is a real workflow that we're actually running as we speak. And that is an example where we use the Lightflow as a pipeline, not to do analysis, but for example, in this particular case, to do data management. So this one runs at our microcrystallography beamline, where we take a lot of files and compress them into a single squashfs file so we can archive it. And I'm not going to the exact workflow what happens, but you see all the typical parts you would expect. You see sequence of tasks. You have tasks that can abort if something's wrong. You have a decision with no yes. You have a parallel task that run down there, followed by a sequence. So all the things I've been talking about is all in this one. Again, a single file describes the whole workflow. And in this particular case, it started with a REST call because we have services at our beamlines that under particular circumstances call that and say, oh, we're ready, compress the data, and there comes a REST call. So again, you have these sort of parts where you have a trigger-like part with a RESTful interface, and you have a pipeline-like part, that's the whole thing pretty much, with all these elements that I just mentioned. So what is Lightflow good at? It's good at distributed processing of tasks with dependencies. We have no single scheduler daemon. It allows you to do dynamic execution of different DAGs at runtime. This is where you can change your strategy at runtime by calling other DAGs, depending on what's going on. The interface is really intuitive. It's just Python collections to describe a workflow, and that's pretty much it. And it has a really low number of dependencies. We don't only have NetworkX, Redis, Celery, and that's pretty much it at this point. Of course, it has its problems. It's because it's distributed, it's really not good to transport lots of data between tasks. So it works well for us for, say, spectra and single images of detectors, but a full 3D data set of the reconstructed dinosaur, you don't want to send this over the network. So it definitely not for that. And it's not good to do fast processing of large data sets in memory. I mean, like you use Python to do it. It's a distributed system. There's no support for shared memory. We have special tools to do that. So you don't want to do that in this case. OK, so if you download Lightflow, what do you get? So you get the core system. You get the Python task that I have been talking about. And you get a bash task that just runs random bash calls that you would like to do. Everything else, we push into extensions. So we keep the core system really lightweight. So at the moment, we have extensions to deal with file systems. So that's the notification for new files and all the typical file system things you would expect. We have a RESTful interface to start new DAGs. And we have an extension for epics. And I think nobody in this room might have heard about epics. But epics is a C++ framework to develop device drivers and talk to devices such as motors and detectors. And that is how we run the facility on a really low level. And we have ways to talk to those devices within the workflow as well. There are a bunch of features I couldn't cover in the talk. So you can have arguments to workflow. So you can start a workflow with different arguments. You can give aliases to data, so you can tag them. You can send tasks to special queues. So for example, if you have a worker that runs on special hardware, so certain tasks should only go to that special worker. And you can stop and abort your workflow, of course. It's available from PyPI, so pip install Lightflow, and you're good to go. Gives you a library and a command line client. Ships with 15 examples, which pretty much cover everything, all the features that we have put in. And that's it. So source code is on GitHub under our Australian Synchrotron GitHub account. So it's all one word, Australian Synchrotron. And then there's a GitHub page also on the Australian Synchrotron, and so on. Thank you.
All right, we have a few minutes for questions here. We'll go right there. I'll be right back.
Hi, thanks for the talk. So you mentioned couldn't process or struggles to process large data sets. In your experience, what kind of the upper limits on those data sets?
I think the problem is that our data sets have the step function. So they're either a few megabytes, and we have no worries with that, or they're a few terabytes. So we don't barely have anything in between in that I could say, yeah, we're struggling. So I would say as long as it's 100 megabytes or something you could efficiently, depending on what your network infrastructure is, you can send over the wire. That's fine. But yeah, typically what we also try to do is the workers have the data. If you have really large data sets, all our workers have the data mounted from our central data store. And so we just use that framework to call tools that run on that data. But yeah.
You mentioned that you evaluated a number of other data flow solutions. Which one was most similar to Lightflow, and what were the specific things that you determined failed your usage requirements with that system?
So I think the closest we had is one called Fireworks. That's from the Materials Project guys. Very similar way of describing a workflow in Python code. But they try to also have a YAML and I think an XML description of the same workflow in parallel. So trying this compatibility between all these things made it really hard to be a bit more flexible on the description side. The other issue they had is they didn't send almost arbitrary data between tasks. They really went basically with file handles or locations to files. And we really wanted to be able to just send and serialize data and send it down. But they came really close. So does Airflow is one example which we really liked a lot. The problem we had with Airflow, for example, is that it's meant for long-running tasks, and we want to be a lot faster. And so, for example, one of their things is they have the timestamp as an ID built into their core. So you can't run anything faster than a second. And that sort of broke it for us. That's what I meant. So we were like, that's so good. And then you have this one thing, you're like, damn.
Cool. That's really great, great stuff to see. I'm wondering though, I mean, it reminds me, I'm looking at my application, which is kind of like a make system, taking files, running them through particular processes, and based on those, do you then do something else with them and so forth. How easy is it for the tasks to redefine bits of the workflow on the fly? Can you say, oh, well, I've now realized that I need to do this extra step? Is that possible?
So so you hardwire that graph as you have seen. You can, by returning this action, the limit as I showed, you can describe a path through your hardwired graph. So you can go, or depending on this one, I go this path instead of this path. So you have flexibility within that. Typically what we do is we use those graphs as building blocks, keep them rather small, and then just have them call each other. And by doing that, you have a really high dynamic because because the idea was there are a lot of workflows that are quite static, like loading a file, looking for permissions, like things like that really never change. So you can have them in one graph, but you have all these building blocks. And so what we do over time is building a library out of those building blocks, which then you can compose bigger workflows out of those, which are then dynamic because you can just say this task now is ready to call that graph. So the graph pops up, that graph calls that graph, that starts. So this is how you get the dynamic in.
So I'm curious if that the light in Lightflow is for lightweight or because of your work in light. But my question is, would you actually want or consider building a GUI, a graphical interface in front of this that would display the DAGs and all that?
Yes, so because it's based on Celery, the easiest GUI to have is just use Flower, which is the GUI for Celery. Runs immediately, because it's all based on Celery, runs immediately with it, so you don't have to change anything. But it doesn't give you a nice overview of your graph and where currently the processing is at, obviously, because it doesn't know about that. We're working on a GUI. So we have a scientist friend who's like using Polymer and WebSockets and things to build one at the moment. But it has never been on our high priority list because it's a system that runs mostly in the background. But yeah, it's definitely on the list of things to do, but had a lower priority, obviously. Yeah.
Do we have any more questions? Very good.
How adaptable is Lightflow for processes that might break or something goes wrong, bad data, that sort of thing?
So the way we have workflows is that we can't rerun a function twice. So that's, for example, something that Dask or similar systems require, that you can rerun a function twice. So in that case, if something breaks for us, we just say everything goes down. And then then you can get notified, then you look up what it is, and typically then you look what it is. So the whole idea of other workflow systems that can run partial graphs again because something broke, we can't guarantee that. And so we don't do that. So if something breaks, the whole system goes down. But at least because it's distributed, it just means that workflow goes down. It has no effect to all the other workflows that are going, that are running. And so, yeah.
That is all the time we have for questions. Andreas, you'll find a mug for you over there as thanks on behalf of the PyCon Australia organizers. Let's give Andreas another round of applause.